we looked at yesterday, and I also showed you yesterday a result with the implicit Euler method, which missed the details in the beginning, but then went to the curves of the exact solution. And you see here what the trapezoidal method does for the same time step. So it's a relatively large time step if we compare it with an explicit method could take. And you see here what happens. It is oscillating. So these are simply oscillations here. So it goes up and down. It oscillates around the exact solution. So you see the oscillations get smaller as we proceed. They will probably sometime later on in time fall on the exact curve, but these oscillations are really annoying. So that is due to what we studied with the amplification factor going to -1 when we take large time steps. So you see it here already at this time step that it can happen. And this is then a feature that is not so nice. Okay, so that was the example I wanted to show you for the trapezoidal method. And you are going to use yourself do some experiments for the other stiff ODE that we had, the scalar ODE by Heath. Then you can also test how it behaves for that. Okay, so then we want to continue, and the point now that we want to look at is how to implement implicit methods. Explicit methods, you have seen that in exercise 2 already, that they are relatively easy. If you have your function f, you can essentially go ahead easily. But here the problem is f contains the unknown that we don't yet know. So that's how we deal with that. So let's look at that. And that is very relevant what we discuss now also for discretizing partial differential equations. So it's the implementation of implicit methods. And as an example, we'll consider here just the implicit Euler method. If you know how to do that, then you can do it also for the trapezoidal method and for the BDF2. So, what do we have to do? In each time step, we have to solve a nonlinear equation. That's because when we write the implicit Euler method in the form that we can see that's an implicit equation, it's a nonlinear equation. We say yn plus 1, now we write everything on the left hand side, minus yn minus h times f of tn plus 1 yn plus 1 is equal to 0. So it is nonlinear when f is nonlinear in y, then it's a nonlinear equation. Otherwise it's linear and we can solve it. It might be more difficult than for an explicit. Imagine we would have a linear system, and we would have to solve this linear system. We don't have to solve linear systems when we use an explicit method. But now we want to discuss the nonlinear equation, so we assume now that the f is nonlinear. And even if it's linear, we'll see that we can also discuss that. But now the unknown that we have to solve for is the yn plus 1. Because it's here, it's nice, that's no problem, but it's appearing here in this, what we assumed now to be a nonlinear function. So then we get to solving a nonlinear equation. Imagine y is a scalar, then it's a scalar nonlinear equation. If y is a vector, it's a nonlinear system. So we do now what we usually do. We define, at least I'm used to that, to define the root of the nonlinear equation as x. So then 13 becomes the following. And that equation we'll call, or I call now, f of x. So everywhere we have yn plus 1, we write now x to get it in the form of a nonlinear equation. X minus yn minus h f of tn plus 1 x is equal to 0. So that's the nonlinear equation that we have to solve. And we have to do that in each time step. And it will change because the solution will change and the time will change. So how can we solve this equation? Well, we can use any method for solving the nonlinear equation. If it were a scalar equation, use a bisection method. In general, we could use a fixed point method, but the method that is usually working quite well for that, and if it converges, if we get a solution, it's Newton's method. So Newton's method would be a good choice for doing that. So we can solve this equation by Newton's method. If you have any other choice, that's fine, but the strong competitor is always Newton's method, because if you have a good initial guess, and we have actually that, because we have yn, the solution at the old time level, that's always a very good starting guess for the solution yn plus 1. So then, if it converges fast. We need only a few iterations, and we shall see in a minute, maybe we need only one iteration. So then, if we do it by Newton's method, then we would get the following. We would solve it as an equation f of x equal to 0, and then we would get the derivative. Now I introduce iterations. That is now because that Newton's method and any other iterative methods. We need iterations, and I call the kth iterate that we know xk. We want to compute the new iterative solution xk plus 1. So we take here the derivative of our function, our nonlinear function with respect to x, the unknown, and we multiply it by the change from iteration k to k plus 1. And that is then equal, on the right hand side, minus f of xk. And then we compute the solution at the new iteration, k plus 1, by taking the 1 at the old and adding this change, delta xk. Then we are done for one iteration. And as already mentioned before, a good starting guess would be for this problem to start with the solution of the ODE at the old time level, which is yn. That is a good starting guess. So then we can ask, what does this df of x look like, this derivative, or Jacobian actually, if we are in the systems. So we can write that, df of x with respect to x. Then we see here how it is defined. Here's x contained here. So we get we call that the identity matrix if we have a system. If we have just a scalar, it's just 1. So that comes from the derivative of x with respect to x. That is easy. And then this does not contribute anything because it's not dependent on x. We have a contribution from here. And here the Jacobian of f will come into play. So we'll get minus h, and then we'll get the df of Tn plus 1 x with respect to x. So that means here we have the identity matrix. And here, this part is what we have already discussed when we discussed the stability of ODE and then later of also ODE methods. That's the Jacobian matrix. Jacobian matrix of the right hand side of our ODE with respect to here we call it x, usually we call it y. So then we have here a recipe by Newton's method. Starting guess, we have here how we do the iterations. And then we need also to stop the iterations at some point. We need a stopping point. And the one that is usually used that is to check the change of the one iteration to the next. That is to change the delta x k. That is the change in the iterative solution. And that has to be smaller equal some tolerance. You would be very try to be very precise. You would try to solve that, say, in little larger than the machine epsilon, say 10 to the minus 10 or something. But that, well, then you would be really do it very, very accurately, but it's often not necessary. And this here is the norm. And you can choose any norm, for example, the Euclidean norm. Euclidean norm, say the norm of x, this would be corresponding then for delta x. That would be for an m vector x, it would be the sum of all components xl squared, and then we would take the square root of that. You could use also other norms, just the norm gives you a measure of the vector. So here that would be the true norm, or the Euclidean norm. And that's what we see here. I think that would be necessary if you really have a very stiff equation. That then you would be probably forced to do that. But for the equation that we have in the exercise, I didn't do it. I used another approach which is much simpler, and that actually worked. And that is using only one iteration of Euler's method. Of Newton's method. Only one iteration. And then that's it. And that has a name. This, if you do it like that, then you get the Rosenbrock type method. Rosenbrock did that for the first time, and you can apply that also for any ODE, implicit ODE that you have, and then you can solve it without iteration. But you're not sure that you are solving the nonlinear equation correctly, so you might get wrong by that. But usually it works. If you combine that with an error control, the time step control that we discussed earlier, with the ODE 45, which has this feature, then it would probably work nicely. Because then you would figure out when things are changing much, and then you would reduce the time step there automatically, and so that you don't run into problems due to the fact that you don't solve the nonlinear equation correctly. But it's a very practical way, and it's used quite a lot in the CFD. If only one iteration of Newton's method is used, we get, in this case what we discussed was the implicit Euler method. But you could also do it for the trapezoidal method or BDF2 or other implicit methods. We get it then as a so-called Rosenbrock type method. Also, we have this idea for the first time. And then we would get the following. So then we would just do one iteration. So then we would directly use the df of x, and we would use just getting from yn to yn plus 1. So then the x 0 then would use then the yn. So then the df of x, we write it now directly, would then be the identity matrix minus h, it's the time step, times the Jacobian matrix of f at the new time level. Now we write them at yn, so we use just that directly dy. So that's the Jacobian matrix of f with respect to y, using the old time level that we already have, yn. So that is then corresponding to this for iteration 1, when k is 0. That is this. Because x0 is then yn. So that is what we're using. So that is multiplying delta x, which is now, in our case, the yn plus 1 minus the yn. So we can call it delta yn. Change in the solution. On the right hand side, we have the minus f of x. Now I took away the f of x. But if you look at your notes, the minus f of x, if you look back on that, it was equation 14, minus f of, that would be minus f of yn in our case. Then we would get yn minus yn is 0, minus h f of t n plus 1 yn, and all with a minus in front gives us then here a plus h f of tn plus 1 yn. So that is what we get. And then we would compute the solution at the new time level that we want, that is really what we want, by the one at the old time level plus this change. So that changes then the change from solution from time level n to n plus 1. So that would be then our algorithm that we would use to implement the implicit Euler method. And that would then be without iteration, but at the cost that we might not solve the nonlinear equation correctly or good enough, say that way. Okay, so let us look at an example for that. Actually now the exercise, the new exercise, and that is the part 2, and that is a chemical reaction with slow and fast reactions taking place, so you get by that different time scale, so that it leads then to stiffness. And what I did, I used this method and applied it by using it at different with different time steps. So in the beginning a lot is changing, so I took very small time steps, then I let, after the initial phase, larger time steps and so on. It goes to 10 to the 11, so very large time. And that is then, I called it implicit Euler. That is for exercise 3. Let's see if we get something out there. Okay, we get a couple of results, and this is the result for this. We are solving for concentrations or mass fractions, how you see it. So concentration of, we have different species. In the combustion process there are different species. In this example there are 3. So here we have then the mass fraction would be the mass of that species with respect to the total mass. So that means the mass fraction can only be between 0 and 1. If it's 1, the whole mass is the mass of that species. If it's 0, it's nothing of that species in it. And this is the mass fraction then for Y2, for the second species, and that goes, it's, oh, I have to show, I have to show you that. Let's see. And that is also the one that you are asked to compute. So here we have the time from 0 to 0.3, and here we have then, say, the mass fraction or concentration, 10 to the minus, let's see, to see, it's minus 5. So it goes up from 0 very quickly, and then it out constant. And you would see also when you apply the ODE 45 that you get a lot of oscillation, that is this bumping back and forth in the canyon without knowing much, and you just get back by the error control. So you get not a good solution, but even with this first order method you get a reasonable solution, and you do even better with MATLAB's inbuilt functions because they are using even higher order methods. And the other figures are concentrations, let's see, for a longer time. This was the time, not just the initial time, and this is for the complete time. It is up to 10 to 11. It's hard to see, but it's up to 10 to the 11. So you see here that that is the species number 3, so Y3, and that is coming from 0 up to 1 for the end time. And the Y2, that is not so well computed because I did not use fine enough time steps in the beginning. So that is at a very low level. So that is, we saw it already, it's from starting from 0 to about 10 to the minus 5. And so I miss details here because the time step is simply too large here. And then it also goes down to a very low level. And then we have the Y1, that is the first concentration, the first species that is starting with 1 and that is consumed totally almost. So it's going from 1 to almost 0 here at the end time, which is 10 to the 11 is here. So it's a logarithmic scale here. So that it means that you can use this method, but to do it better, one would use high order methods, for example BDF2, and one would use a time step control, and that is done in MATLAB. Okay, so then we have seen this example. Maybe that's a good point to look at these ODE methods. So what does MATLAB give us there? So we can look at the help. We can have it already up. We can do it again. Yeah, there it is. And it was the ODE 23S. So now you can try the ODE 45, and that you can do for the first few instances of up to 0 to 0.3 to see what it gives you. Let's see, we have to go a little up to see the. Let's see if we can get that larger. No. Okay, so then we have to take it as it is here. So the ODE 23S is based on a modified Rosenbrock formula. So it's this one here that we discussed. This idea to do just one iteration of Newton's method to solve the nonlinear system that you get in each time step. But here it is of order 2. Because it is a one-step solver, it may be more efficient than ODE 15S, that is an alternative. We'll look at that in a minute. At crude tolerances, it can solve some kinds of stiff problems for which ODE 1S is not effective. So that is apparently a good method for solving stiff problems. And so it is based on the idea that we discussed here, doing just one iteration of Newton's method to solve a nonlinear system in each time step, but it is of order 2. And they say here it is a one-step solver, so apparently they don't use the BDF2 here, but they use then some other method. I didn't look into the details, but there are other possibilities to get second order. So that is the ODE 23S. And the other one that was already mentioned here, that is the ODE, let's see, 15S here, this one. And that is the one just ahead of that. That is a variable order solver based, therefore, yeah. Here, I think the 23S, by the way, that indicates that it's probably using also another method, a third order method. They don't tell it here, but I think it is, to get the error control, like we had for the ODE 45. We have two different methods with two different orders of accuracy, such that the solution difference gives us some indication of the local truncation error. ODE 415S is then a variable order solver based on the numerical differentiation formula. And yeah, optionally it uses the vector differentiation formula, that is the one that we discussed, BDF2, also known as Gears method. You can also have higher order methods than just order 2. That are usually less efficient, like ODE 1, so on. It is a multi-step solver. Okay, so that is a solver that involves not only time level n and n plus 1, or n and n plus 1, but also n minus 1, and maybe even n minus 2. It's a multi-step method. Try ODE 15S when ODE 45 fails, or is very inefficient and you suspect the problem is stiff, or when solving a differential algebraic problem. We have not discussed that. That is when you have not only differential equations, but you have also algebraic equations, and you solve them in combination. But for us it means that this is a choice for solving stiff equations. And as you see here, it is based on either BDF or similar formulas to get higher order. But it uses, it says here, variable order solver. So it means it's the one could indicate that it's first order, the fifth order. So I have not looked into the details, but apparently it's also with a built-in time step control, so that you can, that the solution finds where things are changing quickly and takes small time steps there. But I think it's best when you try it yourself and see how it works then for the problem for the reactions. Okay, so we have little time left. By the way, do you have some questions on exercise 2? Oh, sorry, exercise 3, the new one. We'll discuss that anyway on Monday in the lessons from 12 to 14 in K26 and from 18 to 20 here. And on Tuesday, Rader will have his demo on the topics to come. Okay, then we look at the last part of this survey on numerical methods for ordinary differential equations. By the way, if you want to do this Rosenbrock method, then you need to have a function also for the Jacobian. So that is all. Otherwise you need a function for f, as you already do for ODE45, for any, also for these stiff ones. And when you do it yourself, you also need the Jacobian. But that's just giving a function and giving the elements of this, in that case, 3 by 3 matrix. So it's very easy. MATLAB does it usually without the Jacobian. I think you can prescribe the Jacobian, you can give it for some of these built-in functions, but usually it does it without. I think they do it numerically, so that you can use like we use difference approximations, also difference approximations to compute the elements in the Jacobian matrix. But now, this last part for ODE methods, I just want to give you an idea of multi-step methods. We have already seen one, that is the BDF, 2, but now we want to see others. So we consider here now so-called Adams methods, because some of them are popular in CFD. And the idea is that we integrating the ODE that we want to solve, y prime equal to f of ty. When we do that, we get the following. We get that y of tn plus 1. When we do that integration from tn to tn plus 1, we get simply this difference. So that's by the fundamental theorem of calculus. And on the right-hand side, we then get the integral from tn to tn plus 1 of our function f. And y is of t, we have to do this integration. And that is where the approximation will come in. We don't know that yet, this function. We want to determine it at the new time level. And the idea by Adams has been to try to get approximations of this behavior of f of t, y of t, knowing what we already have or what we want to get. So, if this is the integrand then here, this f, if you can write it, if t of y of t is approximated by and I call it an extrapolating polynomial. Extrapolation means when you try to predict something, you know something in a certain interval, and you want to predict something that is outside. You want to go outside, extra outside. So that by a polynomial, then we get we do it for one, we get an explicit Adams method. So to see that, we look at an example. And the example is the following. We imagine we have this f that we want to approximate. Here we have time, and here we have the f that we want to approximate. Actually, it's the f of t, y of t. We imagine that we have, say, we have a couple of time steps, and that we are at time level tn, and then we assume that we have also time level tn minus 1, and we want to determine what is going on at tn plus 1. What we imagine is that we know, we call this here fn, and that we know the fn plus 1. So the fn is now standing for f of tn yn. So that is something, here, sorry, this is a bit wrong. I got the indices wrong, sorry. This is fn minus 1, of course, and this is fn. The fn plus 1 we don't yet know. So this is fn minus 1, this is fn. And those we know. That's we assume. We are not at the initial condition. Of course, again, we need also for these methods, we need methods to start them. For example, if we have a method that involves 3 time levels, we need 2 old ones. So we need then a one-step method, say the Euler's method, for example, whatever, to get a solution at the first time step, the first time instant, t1. Then we know t1 to t0 for the initial condition, then we can use it. So that is something general. But now the idea here. The idea is now to approximate the solution, the f of ty of t by a polynomial. And here we use these here. So we use what we have here, that we use, and we are interested in this interval. So what we do, we extrapolate that. We take that, we continue this simply. We assume that we can continue that. That is something that we know. We can get the slope from that, and then we simply assume that we can continue it. If we had one more, we could have a parabola, that we would be able to continue it inside the interval where we don't know yet the solution. So then, in that case, we can then assume that we approximate the function in this part here by the polynomial, by the following polynomial. Let's see. I think I take more space on the other side. So what we do is we approximate our right-hand side of the ODE, which is then a time-dependent function, by a polynomial in T. And in this particular example, we do it by starting from Fn, from here, and then continue with the slope that we have determined by what we already have. So we can express that in the following way, that we take the slope is then Fn minus Fn minus 1 divided by h, because the grid spacing that we have here, both in here, that is h, and also here, that is h. And watch again, it's the same h. We don't allow now for changes, because we need the time level before. And then we multiply by t minus tn. Then we have a first order polynomial. We know that because we know the solution Fn and Fn minus 1. And then we can evaluate the integral over P of t instead of f. So then the integral from Tn to Tn plus 1 of this, I call it extrapolating polynomial, can be done, and we will get, this is an exercise of calculus, h half 3 times Fn minus Fn minus 1. And then we can get the solution from that. Because then we approximate the integral, just put it away, by this integral over the polynomial. So then we get, that is the method that we get, that the solution, the new time now we introduce this notation for the numerical solution of the ODE, that, and then we add, instead of the integral over the exact f of t, y of t, the integral over the extrapolating polynomial, and then we get what we have here, and that is then 3 times, now we write the Fn explicitly, that is Tn yn minus Fn minus 1, that is f of Tn minus 1, yn minus 1. So that would be then the method that we get, and that has a name. It's called the Adam-Spechford method. Adam-Spechford method. That people have been using quite a lot for incompressible Navier-Stokes equations. So just briefly, the En is order h squared, so that means it's a second order method. And the stability domain is again a little bit difficult because we have it's a two-step method. So but the stability domain turns out to be somewhere between 0.75 I and minus 0.75 I, and here we are around minus 1, and we go roughly, it's roughly like that. So that is roughly the stability domain S of the method. So it has a small stability domain, even smaller than the explicit Euler method, but it's second order. Okay, and if we would use, instead of an extrapolating polynomial, an interpolating polynomial, it would mean that we would take the y, the fn plus 1 into account that we don't yet know, but then we would get an implicit Adams method. And one simple example is when we just would with these here, we would get actually trapezoidal method. Okay, but that should be enough to give you an idea of ODE methods, of their accuracy, their stability, and also what we discussed for implement, how you can implement them. Now it's your turn to get experience with them. And then you have already started with exercise 2. Now with exercise 3, you'll see then also how you can solve stiff problems. Okay, so then we'll meet on Monday in lesson.